Good morning, everybody. This is Simple Simulators with Generator Coroutines and Pandas. My name is James Powell. We're at PyData New York 2023. It is Wednesday, November 1st, 2023. If you like this presentation, I give a lot of presentations online. In fact, we have a YouTube channel where we post all of these. Feel free to, like, subscribe, or whatever people do on YouTube if you want to see more of these kinds of presentations. If you don't, however, feel free to also just give me abuse in the comments on YouTube, because I think that's also what people do on YouTube. The goal of today's presentation is to share with you some simple approaches using nothing more than just pandas and Python for building a library that can solve some interesting financial problems. Our actual learning goal here is not necessarily to build these kind of libraries, because even though this is derived from real paid work that we have done, for the most part, this is probably not the majority of what your work, everyday tasks look like. Instead, our goal is to understand a little bit more about the fundamental tools that we use. Where do generator coroutines really show up in library development? And importantly, how do you actually write a library that ingests and returns pandas objects, which I think pretty much everybody seems to get wrong. Anytime you see a function where it takes a data frame and the data frame has to have some specific name columns, there's something amiss. And so let's take a look. The general motivating example is we want to build a library for portfolio construction, some kind of simulation. So don't think high frequency trading, because if we were doing high frequency trading, it's almost certain that we'd write this code in C++ or in Java. If we're going to write this code in Python, then we're going to assume that performance may be important insofar as we'll use pandas or NumPy as opposed to pure Python, but where there are certain bounds on the performance that we need. And so a realistic use case for this would be something like mutual fund construction, where every day you look at the market and you look at the 90-day returns, and then you figure out what comes in or what comes out of that portfolio. You do one trade, you don't really care about execution because you don't handle the execution side at all, you just send it off to a broker. And this is a fairly reasonable and very realistic example. Another example might be something like this, but for much, much lower frequency assets that you might trade, like fixed income assets, where you can think that a lot of those may still be traded by human beings getting on a phone and negotiating a price with another human being. At that scale, we may discover that Python and pandas have sufficient performance for what we want. That is to say, we do care about performance, but there's an upper bound to this. So what we want is moderate performance for backtesting portfolio construction over, let's say, 5 years with a very simple strategy where we get that computation done in, say, under a minute. If, of course, we want to do some kind of high-frequency trading or signal analysis, then definitely the approaches that we see here are not appropriate. However, the trade-off for the slow speed that we get from using Python, or for Python being a major part of this, is that we will get some high generality. And so likely in that case where you're doing some kind of like mutual fund construction, the strategy that you use to construct a portfolio may be arbitrarily complex. It may not be as simple as take these time series and do some analysis as fast as you possibly can and then do a buy or sell, but it may be a very complex analysis saying, we have some unequally weighted portfolio and this is how the weighting is structured, and we have entities drop out when their market performance goes under a certain metric, unless it's under some other condition. We need to have a certain cash holding, and we have to deal with regulatory concerns and so forth and so on. Of course, when we talk about things that are regulatory in nature, we do have unbounded complexity, because the only limits to the complexity of anything that's regulatory in nature is the creativity of lawmakers and their limits for what they think is acceptable to pass in legislation. One other important aspect that we have here is, and I think this is a very important aspect that we don't see in a lot of software that's built on top of pandas, which is we want to be very much supporting what you might call foreign data. So you've all used some tool that a coworker has written for some kind of analysis, and you just took a data frame that you read in using a read CSV, you passed it to the function they gave you, and it blew up. And your coworker said, oh, no, this thing can't have an index. Oh, and the columns have to be named this, and this column has to be this specific D type. And you say, well, you know what? This is not really working with the data as I have it. It only works with the data that you had when you designed this thing. But if you think about this kind of problem, it's very likely that an analyst is going to have some data file that they've pulled from some resource that they're going to want to analyze. And as a consequence of that, who knows what the column names are? Who knows what the D types are? Who knows what other index level data there is? And we want to be as resilient or as flexible to work with those structures as possible. Finally, we want to avoid certain esoteric things that we can do in pandas. There's one particular core to this problem that is very tricky to solve, and we may be able to find some esoteric mechanisms, subclassing Python built-in types, or subclassing a pandas.Series or a data frame, which, by the way, is possible, but I couldn't really give you a sense of how much effort that would be. Instead, we're going to try and make this reasonably easy for a user to pick up and use, subject to them, of course, knowing some basics. What is a generator coroutine? What is pandas index alignment? But beyond that, what they can learn online from any YouTube video on our YouTube channel, they can go ahead with this. And there's a couple of questions that we'll answer about generator coroutines, pandas, and so forth and so on. So let's start off by thinking about how we'd represent financial data. Well, here, if we're building some kind of simulator like this, there's pretty much two types of financial data that we want to be able to represent. The input data is going to be some kind of market data, and the output data is going to be the trades that are constructed. And a very naive way for us to represent some trades that are performed is to represent them as a data frame, where in this data frame we have prices. So we bought something at $10, $20, and $30, and we have volumes, where we bought 100 units, 200 units, and 300 units, and maybe we have some indexing. So here you can see these are maybe just common stocks that we can purchase. And in fact, I've given a lot of presentations where we use a structure that looks more or less like this as the core example. The problem is that this is a little bit phony baloney because, in truth, this is redundantly encoding extra data. And in truth, what we'll discover when we try to build structures from a input set of pandas data frames or pandas.Series is that the larger the structure that we give it, the harder it is for us to actually reduce the total number of assumptions that we make. And so, even though this seems like a reasonable way for us to model this problem, and it has a certain amount of flexibility associated with it. For example, if we wanted to measure buys and sells, we could say, well, maybe the price is always positive, but the volume might be negative. And if we want to do simple financial analyses here, like what's the total volume that we have, we do a group by the index, grab the volume column, and do a sum here. And you can see, oh, that's our total holdings in each one of these names. We could even do a weighted average price and things like that, a weighted average buy price and sell price. And I've done a number of presentations on just how you'd perform those computations and what those tell us about pandas. But one of the problems here is if we end up writing a function that takes a data frame. So for example, we'll have some function called market value that takes a data frame like this, and it assumes that we have particular column names. We've already violated that first constraint of working with foreign data. Because who's to say that the data frame that somebody has given you that's a trace of executed trades pulled from their broker that you're then going to feed into your system to do some sort of plotting or some sort of analysis on has columns in exactly those names. And who's to say that you don't have to do some additional analysis on that? For example, the prices may need to be adjusted to take into account splits or other corporate actions. In that case, of course, you might think that maybe that's incumbent upon the user to actually model themselves. But it just really feels really hokey when somebody says this function requires a pandas structure that has this column with this D type and this column with this D type. And it feels hokey in the same way that if somebody gave you a Python function and the Python function said you have to have trades, and it's a list of a dictionary of a list of a string and a tuple, and this has a string in here. The deeper and more complex this thing gets, the more you'd say, hold on a second, how am I even gonna know what to pass in? How am I even gonna make this reasonably general? Similarly, generally, if we wanna work with foreign data, we wanna make it easy for somebody to keep that foreign data on the foreign data side. Consider this circumstance. When you're writing some kind of library code, if we want to set out a very stark dichotomy, we could say you're either writing that library code where you are the most important thing in the user's life, in which case anything goes. You give them a crazy signature, you give them any structure you want, you're the most important thing in their life, they will abide by that. Or, on the other end, you're the least important thing in your life, in which case they will not countenance 1 minute of having to restructure their data to give that to you. Or, what happens very commonly in these libraries is, the original data structure has some additional metadata associated with it. For example, their original data doesn't just have the ticker names, but it has the ticker names and maybe it has some dates as well. So this might be some kind of multi-index. So here, we'll do a multi-index from arrays, and we'll give these a date range as well. So here, let's do a date range from January with 3 periods. And here, of course, we have to give this as a list of 2 entities. And this is a very reasonable thing that they may start off with and that they may give you. And you need to make sure that you return that thing right back out in the same way, because they don't want to have to say, oh, I gave you these rows and you stripped off some important metadata that I have, so now I have to reassociate your output with the thing that you returned to me or with the thing that I had to start with. And it may not just be 2 levels on the multi-index. They may have a portfolio. Maybe they have multiple traders, and the original data is Alice traded this, Bob traded this, Charlie traded this with this date and with this ticker. And so the greater assumptions that you put on them, the harder it is for them to actually use this tool. And if you're not the most important thing in their life, they will not countenance all of the hoops that you're making them jump through. And so if we really think about pandas, what is the simplest possible pandas structure that we can operate on that's not a pandas array, because nobody actually uses pandas arrays as first-class entities. It's just the thing that you find when you dig down into the tool. It's a pandas series. It's my belief that for the most part, any library code that operates on pandas probably should first and foremost, wherever possible, only ever take as its inputs pandas series and returns as its output pandas series. So if we were to allow this structure, I would say that even though it seems a little bit silly, what we should actually do is we should take the volumes and the prices as 2 input data. And you'll say, that's strange. We could just do the single DF with 2 different columns. How is that different? But here, you're forcing the user to extract that from the data frame, which is a zero-cost operation, or effectively a zero-cost operation. And you're not requiring that they name this thing anything. You are, however, requiring that they keep some sort of indexing here. And unfortunately, I really think that if we're going to talk about the signature of any sort of computational unit that is built on top of pandas structures and returns pandas structures, what you really want is to specify this is a pandas series, if possible, or a collection of pandas series. The D type, I think, is appropriate to say. These are numeric values or not. And whether they are capital IN64s or lowercase IN64s, maybe that doesn't matter as much, especially if you exercise just a small amount of care, because as you all know, a group by unstack and a pivot table with a capital IN64 D type may give you slightly different operations depending on whether you have that fast path where it'll upcast into float 64 and downcast and you lose data or not. And so as a consequence, I think what you can reasonably assume is I'm taking a pandas series, and that pandas series has this particular indexing. And I think where you can maybe get away with asserting that there are certain names of the levels of a multi-index. And so the way that I want to represent financial data in this problem is very slightly different than what we can see here. What I want to do is I want to represent all financial information as just a pandas series. But how do we do that? Because every trade has 2 parts to it, doesn't it? It has what you bought and how much you bought it for. AAPL at $300 a unit. How do we represent that as a pandas series? Well, consider one other interesting aspect of this is when we think about a pandas structure, we often think about some entity that has, like a pandas data frame, an index down the rows and some kind of indexing across the columns. But usually, anytime we do anything programmatic on a pandas structure, we're always doing it programmatically down the rows, but structurally across the columns. In other words, we have some analysis that says take this column by name and then do a .sum or a .group by operation down the rows. And so one thing that we see as a very common and intuition for the use of pandas is that for a pandas series, or for a pandas data frame that is, the columns are some kind of structural entity and the rows are some kind of data entity. Well, if we think about structural versus data and that dichotomy there, one other thing that might impinge upon us is that anytime we have an unknown number of entities, that's always a data problem, never a structural problem. That's why, for example, if you have a CSV file and you have 3 columns in row 1 and 5 columns in row 2 and 2 columns in row 3, that's not CSV. CSV is always a strict number of columns, or each column means something because it has a fixed structure. Well, if you think about it, an actual trade that may be performed in the market is not necessarily the price and the volume. This is assuming a 2-leg trade, where for this 2-leg trade, I trade one set of units of some asset, and in exchange, I get some units of another asset, where that other asset is just a specially marked asset, denomination of a currency. This is actually a 2-level trade. This is 10 units of apple equals 100 US dollars. In fact, what we can do is we can devolve this financial data into a series where you have not 2 legs specified, but an arbitrary number of legs specified with arbitrary grouping within the index, and you're just looking at volumes. And so for this same example, the way that I think we would represent this, if we wanted to build a library for these purposes, is we would represent it like this. A series with every value. And these values would be, let's do like this. We'll actually pre-compute these for you based off of whatever the prices are. And here, it would look something like that. Now here, this is going to be a little bit silly, but we'll assume these things settle in some weird way. So you'll bear with me the example. And of course, we need multi-index. And of course, date range. And of course, capitalization. It's always something, right? Now, here, what you can see is this is a little bit phony baloney, because here you can see that maybe there's like a 3-day settlement period, very common in fixed income for bonds, maybe a little bit phony baloney for this particular example, but you can see that's how it represented. Now, interestingly enough, we can see one interesting aspect of pandas. What do stack and unstack actually mean in pandas? Melt and pivot, I don't think they mean anything. I think melt in pandas is what happens when somebody accidentally puts some things that are supposed to be in the index in the columns of an Excel spreadsheet, and you have to load it in. But I think stack and unstack actually have real semantic meaning. I think what stack and unstack mean is you have some data, and whether or not that data is considered homogeneous is subject to a particular perspective. Is this homogeneous data? Yes, from a strict data type perspective, they're all integers, they're all floating point numbers. But is it homogeneous data? Well, can I sum up units of Apple stock together with units of US dollars? No, that's meaningless. And so, as a consequence, what you can think is, if we want to do those easy sums, we do them either as a group by operation or as an unstack operation on that first level here. Let's name our indices, or levels of our indices. So this is asset and date. There we go. So we'd unstack the asset and then perform a sum. And you can see, as a consequence of this, we got another calculation for free. We now have not only what our portfolio looks like, but what our cash holdings look like, which of course for the portfolio construction analysis is a very useful thing for us to know, because we may be limited based off of needing to retain a certain amount of our cash holding in order to keep the strategy alive, or whatever rules we have. Here, what you can see here is this is a common thing. The stack and unstack are about taking some single column of data and saying, you know what? It looks like it's all the same thing for one perspective. For example, they're all trades that moved a volume of some particular asset, and turn it into multiple data sets that each have some heterogeneous meaning. Oh, actually, we can't add MSFT to AAPL to USD. That's not a meaningful thing to do, so we have to convert it back and forth. Now, with that said, I think we end up with something that's quite interesting, which is we can perform a lot of financial calculations quite easily. But there's one detail to this that is going to be a bit controversial. Are you ready for it? Some of you look like you're ready for anything. Some of you have no idea what's going on so far. I'm not sure what you bought into. Here's the thing. I think fundamentally everything has a price, and you multiply times the volume and you get what it's worth, is total BS. That's not how, even in an example like this, anything actually works. I think, especially since if you consider the strategy construction is an ahistorical thing. It's counterfactual. You're saying, given this pricing information that I have for the market, how would I construct a portfolio and how would that portfolio perform? But I didn't actually do those trades. It's not a real thing. I can't magically wish into existence a trade that happened in the past. Instead, what I have to say is, assuming under these circumstances I perform these trades. And a limitation of that analysis is, if you trade in ways which would have otherwise affected the price, your portfolio analysis is going to be dodgy, right? Like if you short squeeze something, the prices that you're using historically don't mean anything anymore because that's not what the price actually would be. The price would be affected by that. In fact, in general, if you think about it, the price at which you buy something is based off of more factors than just one singular scalar price. Because if I go to you and I say, how much is a peanut? You'll say it's 1 cent. If I say, how much is every single peanut in the world? Well, it's not 1 cent per peanut anymore. It's much more expensive because somebody needs to have their peanut butter and jelly sandwich for breakfast. And so, yeah, it's a good breakfast. And so, as a consequence, what we actually want to have is some mechanism that abstracts the notion that the market has the ability to price things in some opaque fashion. And within that, we may still make simple linear assumptions for the purpose of this example, but still allowing us to violate that linearity or to add in some additional complexity, or for example, to say, if you attempt to trade something where you exceed the trading volume that we historically see in our backtesting data, we will not allow you to perform that trade, or if you do more than 10% of that, we'll not allow you to do that trade, because then you would have affected the market and the analysis is no longer valid. You can't have bought 1 million units on a day where people only traded 100 units and still use the same pricing data and assume that it'll mean anything. And so, as a consequence, what I think you would want to do here is you need to have an actual class to represent the trading environment. And the reason for this is, when we talk about classes in Python, there's a lot of different things that we might use these for. For example, we often use classes in their simplest form, data classes, or even what we can construct with the name tuple, just for data structuring. We have some representation of some information, and we want to do the dot and then the name of what the thing is. So, for example, if we were to represent a single trade in pure Python, it's very common that if we were to represent this in pure Python, we might say, you know what, this is a trade and it has an asset and a volume. And we'll just do it for data structuring purposes because it's a little bit nicer than using a dictionary or using a tuple. The other reason why we might use a class is if we want to represent visually to a user that there is some opaque entity here that has some defined API. The environment can do something, but we don't really know how it does something. It encapsulates that behavior and hides it from you. And also, importantly for this example, gives you the ability to swap out the market environment. So what we can write is a very, very simple market environment. And if you think about it, a simple market environment should have the ability to execute a trade. Now, the naming here is going to be really, really hokey because I can't come up with good names for these pieces. But if you think about it, if you start with the actual trades that you have as a pandas.Series. So let's say, and we actually need to represent it like this, 100, 200, and negative 150. And we'll say this is Apple, Microsoft, and Apple. And we'll make that a multi-index in a moment, just so that we can represent something akin to what we would actually want to look at for this. So here, let's make this a multi-index with a date range. And we'll say that this is asset and date. So we need a multi-index from arrays and a date range. There we go. And of course, we need this as well. And here, let's actually format this code slightly nicely. There we go. And you know what? Honestly, for these structures, I usually care more about the index than I care about the data. So just to make a point of it, I'll actually specify the index. Who creates pandas.Series specifying the keyword arguments for the index first? This is a very strange presentation. Anyway, here's what we have. And of course, when you want to name these, we always want to name our layers of our multi-index. So this would be asset and date. So there we go. So here we have, and also, you know what, if we're going to name things, we might as well name this. And this is a volume. So there we go. We have our pandas.Series representing these. Well, I think we want the environment to be able to execute these things, which means give us the other side of the trade. Go out into the market, tell us what it would cost in order to execute these, and give us the other side, how many dollars we'd have to give or receive in order to actually execute this. And so what we could think is that the environment's going to have some notion of its market data. Now, if you think about the market data, this is one area where we might violate our be open to foreign data assumption because, of course, that's going to be so tied to how the environment is going to operate that we might need to put some assumptions on it. But largely, if you think about what the pricing data looks like for a very simple linear market, well, it's going to be pretty easy. Here, let's make a data class. And let's make this a data class. And let's just give it some prices, which would be a series indexed off of the date and the asset, as well as what the observed price was in the market. Close price is a very common thing we give for Yahoo Finance or Google Finance, which is just about the level of sophistication of the example that we're looking at so far. So we'll create an environment. And we'll give it some prices here. And we can take, let's see, how many days do we have? We have 3 days. So here we can do the following. So let's say this is trading at, it's like $300 for one, $400 for the other, 325, 425. They all did pretty good over this period of time. And we'll do a multi-index from product with our assets across. We have 3 days, don't we? So let's do this over 3 days. So these two stocks did very well. Technology did very well over the period of the analysis that we're looking at. So there we go. Okay, and finally, let's name these. This is asset and date. And so you can see we do have some assumption that we're imposing upon our user, specifically that their user data is some kind of pandas series with some kind of numerical contents that is indexed identically to the assumption that we have for what the market looks like, specifically something like this. And this should be, yeah, that's good. That's good.
What's the name?
Oh, the names, yeah, thank you. So there we go. So here's our trades. Here's our environment. And then we can have the environment go and execute these. And this actually ends up being fairly straightforward to do. Now do note that if we wanted to represent a real environment, we wouldn't represent these as singular prices. And so we might bend the rules very slightly in this case and either represent this as the two sides of the price. Obviously, buying something and selling something do not occur at the same price. We've all experienced that when we go overseas and we look at the money exchanger and you're like, hold on a second. You buy US dollars, I can never understand which direction it is. You buy US dollars at 33.2 and you sell them. And whatever the case is, don't worry, they're just ripping you off, you know. Okay, if you get anything from this presentation, here's the thing you need to know. If there's a money changer inside the security area of the airport and a money changer outside the security of the airport, never do it on the inside part because they always rip you off like nobody's business. Always go outside and they'll give you a better price because they know you're a captive audience. They know you don't know what's going on. They know you're desperate to get a cab. Never do it on the inside area. Same thing with SIM cards. So here we might have a series, or we might simplify our life slightly and do a data frame where these are our buy prices and our sell prices. And of course, for this example, we'll create a very simple spread here of just a fixed dollar. So something like this. And so we can always buy higher than we can sell. Otherwise, we'd be able to make infinite money, right? So we might represent those as some kind of data frame structure, but you can think that it's just two similarly indexed structures. From that, we can then determine what the actual executed price is. And this requires a little bit of pandas mechanics. So rather than do it inside execute, I'll show you how I do this against just the data frame itself. It's a good opportunity for us to practice some of our pandas mechanics. Now, what we know is when we have, and let's create this with a none here. There we go. When we have structures that look like this, how do we actually figure out what the executed price was? Anybody know how to do this in pandas off the top of their head? This is actually something that turns out to be surprisingly slow. And the topic of performance hasn't come up in too much depth with any of the work that we've done so far. We're kind of assuming if we're using pandas and we're doing aggregate operations at pandas, everything's at pandas speed, which is fast. What I'm going to show you here is relatively slow, but in fact is not really meaningfully slow. In part because if we were to build a system like this, these are aspects that we could easily revisit after profiling and drop down into Python, or Numba, or whatever other tool we want, into Rust, into a C extension module, whatever we want to do. Unlike another problem we're going to look at in just a moment. Well, what we want to do is we want to actually figure out what the price is for each one of these trades, which is relatively straightforward to do because we just need to figure out what the direction of these trades are. So we'll take our trades and we'll just get the sign of these trades. That'll give us whether this thing is a positive or a negative, right? And if it's a positive, then it means that we bought it. If it's a negative, that means that we sold it. Then what we can do is we can take a series that's indexed off of these And we can do a dot lock operation on this. So let's do a positive is a buy, a negative is a sell, and we can do a dot lock off the sign of our trades. So there we go. We have buys and sells. So we know exactly whether these are buys or sells or not, right? We can just grab that. We don't actually care about the index anymore. So we have that layer. We can take this result and we can construct a multi-index from this. So what we'll do is we'll construct a multi-index from the buys or the sells, from the assets, from the asset, and let me see what asset, date. Okay, so asset, date, and buys and sells. So now we have a multi-index that matches what we actually want to do a lookup on. And here, all we have to do is we just stack that level. Now we're going to name some things here. So here, we're going to name one more piece here. We're going to do a set axis or rename axis. Columns equals direction. So we know the direction of the trade. And then that way we can give this names, asset, date, and direction. Like that. So now we can perform a lookup directly from this, and then we can just take our prices with the stack direction, or we could even pre-compute what the stack direction looks and do a dot lock here. So that's the actual prices that these were executed at. Once we know the prices, we can just take that result and multiply that times the actual trade volumes, and that's the USD. We just have to reset the axis. That's how many USD that we executed these trades for. Now, of course, we may have to adjust the date to account for settlement periods or whatever, but it's a relatively straightforward analysis. Note one interesting aspect of this. What if the source data originally had extra index layers because, for example, we're saying there's these books and these portfolios and all of this other structuring? Well, it doesn't actually matter because the code that we've written is actually fairly transparent. So, for example, if we have multiple portfolios, so here we have Alice, Bob, and Alice. So Bob did one trade and Alice did two trades. And of course, oh no, we need to do this. This is a from product, so let's do it like this then. We're gonna change this very slightly. We'll do two dates, 2 and 2, and that should give us, we need two more. Oh, and by the way, that's in the wrong place too. It should be up here. So this is Alice and Bob and Alice. There we go. And then of course here, this should be up here. So if we have that, it'll just come straight through on the other side. See? We have it just come right through. Now we might have to remove things like that direction, but we added that in through that stack operation, so that's not really a big deal. We know that it's there, so we could just drop that level very easily because we explicitly added that level. So there is an assumption, of course, that we don't have some duplicate levels, or you don't have direction, and we could do some tricks there. For example, we could name this something that they're not likely to name it. That way we can avoid overlaps with their column names or with their index level names. But here, let's take this result and drop the direction level. And what we get out of this thing is actually transparent to foreign data. If they had arbitrary numbers of additional levels here, the only thing that we've done here that's maybe a bit dodgy is we've reordered them. But note, this analysis is going to be expensive for two reasons. One of them is this lookup with the multi-index is surprisingly slow when you actually measure it. I don't know why that is. Even if they're lexicographically sorted, it's still very slow. But if you think about it, it's a very simple operation to code up in a little bit of C. You're just scanning through if these are sorted structures to match for the exact entities and just creating a new structure on the side. And so you could drop that part down into C pretty easily, or into Rust, or whatever you want, quite easily. So I'm not worried about the slowness of that. There's one other aspect of this that's a little bit slow. We're making use of index alignment to match up the two indices. We have assets and we have dates on both sides of these structures. We index align them and get this result. So we do the dot lock in order to get a properly indexed structure. However, we know that this structure is aligned already because we did a dot lock to get the index in the form that we want. So this is maybe one place where we could reliably and generally just do a dot values. And when we do a dot values, we're going to lose the levels on that. So we'll do the dot values on the other side. So we'll do trades there, and we'll do a .values here. And if we do the .values there, we don't even need to drop the direction axis at all, or the direction level at all. And you can see we pass through their layers or their multi-index exactly the way they gave them to us without any additional mechanics. This is something that you see, you don't really frequently see that there's some difference between A times B and B times A as a consequence of the index alignment. And the reason for this is, for whatever reason, pandas users seem to be very shy to use index alignment for anything. They just reset index. And they do dot values all over the place. But here I think is a legitimate use of dot values to avoid a spurious cost of an index alignment, and also to preserve the input data right back, or certain aspects of the input data right back out. And so here you can see we can execute these trades. And a very interesting consequence of this approach is the total portfolio is now just the concat of these. So if we take the original trades and just concat it against the executed values, this gives us our full portfolio. Now, there's one more slight detail we have to do here. This result has a wrong value for the asset because it's telling us, oh, we bought Apple and then we sold Apple. Well, one tiny detail here, and this is going to be a little bit clumsy to do. Here, on this result, we want to do a set axis. And here's one place where fundamentally we'll run into some limitations of writing code using pandas where it's library code, which is, unfortunately, the pandas API, despite being very coherent, it has a very clear mental model around index alignment, is very inconsistent in terms of how it actually gives you mechanisms, methods to interact with that underlying coherent model. And as a consequence, what I want to do is I want to take all of those asset values for the last three and turn them to USD. I want to change the value of that. I can do that with a set axis call, but I can't do that on just one level. I can drop a level, I can reorder a level, I can swap a level, and just let's remind ourselves of one of the absurdities of pandas, because this is what I mean by the thing being coherent, but not particularly consistent. If I have a data frame, I can swap levels, or swap level. I can reorder underscore levels. Why is there an underscore in one of them and it's plural, and there's no underscore in the other one and it's singular? How is that consistent in any fashion? But fundamentally, it's a coherent model. It's all just operating on the index and doing some operations with the index. It's just that the API is a little bit all over the place here. And unfortunately, if I can swap levels, I can reorder levels. Who wants to take a bet here? Is it drop level or drop levels? It's probably drop level, but I bet you can pass multiple levels to it, and it works. So this is a drop level, but you can actually drop multiple ones, I bet. I don't know, look at the documentation. But you can't add a level, and you can't set a level. And so there are these little bits and pieces that are missing. What do we do about that? Well, one of the answers is we go into the pandas code and we help out the pandas core developers by implementing these missing functionality. And I think that is a very worthwhile thing for us to do. One thing that we should recognize, especially for tools like pandas, they are tools under active development. They are not complete. There's still room for improvements, and there's still room for ergonomics. However, if we're working on this project for real, we might have something of a crisis here, because we have the right thing to do, which is to go and implement the missing operations, and we have the expedient thing to do, and the right thing to do may take an unbounded amount of time. We don't know what it takes to get something approved as a PR into pandas, and the documentation requirements, and the testing requirements. And we have a user who wants the system we're building right here, right now. So I'm going to show you something, and this is also very controversial. Hopefully, some of you are aware of pandas extension mechanisms. So if we go into pandas, we can go into pandas API extensions, and we can register a series accessor. We can actually register DataFrame accessors, series accessors, and index accessors. And in this particular case, I want to register an index accessor, but I'll show you a series accessor. The way this works is, this is a decorator that operates on some structure that gives you extra namespaces under pandas DataFrame, pandas series, or pandas index. So for example, you ever wonder how you do like series.dt to get the datetime operations, or .str to get the string operations, or .cat to get the categorical operations? You can add those yourself. Now, One question is whether or not we should have orientated the entire library that we're writing in terms of those. So you have like a .fin for financial operations, but I don't think that's really what we want to do. We really want to preserve the generic meaning of the pandas.Series as just being operations on D-typed values, not on business-typed values. But here, what we can do is we can do our own namespace. So let's do a namespace like this. Let's make our lives easier by making this a data class. This thing gets an object, which will be a pandas.Series. Let's create a series for our program. And we'll create a very simple series with 1, 2, 3. Let's print out this series like that. And by virtue of having done this, we now have our own namespace. Now we need to register series accessor data. That's good, that's good. Oh, and we have to give this a name. So it looks like ext, like that. There we go. So now we have our own namespace. And you can put any arbitrary operation, so we can extend the operations that are provided to us in pandas. This is, I think, a preferable option over subclassing a pandas.Series or a pandas.DataFrame. There are genuinely packages out there that do that. GeoPandas, as I understand, subclasses the pandas.Series or pandas.DataFrame. Between you and me, I don't actually know how much effort it is to maintain that. And another important aspect of writing a library, other than are we the most important thing in our user's life or are we the least important thing in our user's life is, how important is this library to our lives? Do we really want to subclass a pandas.DataFrame and then have to watch pandas changelogs for the rest of our life for changes to the pandas changelogs and then require that they make changes to our subclass entity? Probably not. Because this is probably not the most important project. This is probably the project that we do. And then in terms of how it's going so far, we probably either leave or are fired the next day. And so our ability to maintain this is quite minimal. Instead, what we might do is we might look for the lightest mechanism to extend this. And so the registered accessor just adds an extra namespace there with a very narrow mechanism for this. So we don't have to track changes to the underlying data types. We just leave this as just regular old pandas.Series, regular old pandas.DataFrames with extra accessors. Now, my view is, if we do something like this _ext, we create something that's very easy to search for in source code, and it may not be a bad idea, even though it's somewhat controversial, for us to identify what is missing or what is inconsistent in the underlying pandas API, and to sand down those edges for our users today, while hopefully simultaneously trying to upstream these changes by doing something like this. So if this is an index accessor, like that. Of course, this won't work anymore. This has to go on the index. We might do something like set level. And here, we'll take the name of the level and the values. And so now, we give ourselves a nice place to put the missing mechanisms or the things that we really wish pandas had in a way where if this actually does get upstreamed, we can grep through our source code and look for every _x or whatever we want to name this so it really stands out, and remove this when pandas actually supports the thing that we want. I think this is a compromise, and I think this is relatively controversial, but in practice, this may be the best option that we're left with, especially if we have a looming deadline for the tool that we're building. And so here we might do something like this. Now I'm going to do this by hand just to show you how much of a pain this is. Here I actually need to not do a set access, but I have to do a pipe. Another inconsistency in the pandas API is sometimes you can pass in lambdas, sometimes you can't, and other times you have to compose with a pipe. So here we'll do a pipe operation, and so that we can access the existing index. We'll do a set access on this thing. We'll do a multi-index from, and this is so hokey, from arrays, where we have to just repeat every value of this. So asset, and I think we have to get the order of this right too. So we probably have to do this programmatically to make sure that we get the order of this and anything else that's in this thing right. But I'm going to hard code this for just now. So we really need to do this programmatically, because otherwise it's not correct. And then for asset, we just do USD times len s. And if we did that right, there we go. And you can see, and we got this wrong with the levels of this thing, portfolio, asset, date. So here, This is why we have to do it programmatically, because otherwise we get this wrong. But then here you can see we've managed the execution. Well, one interesting thing here is, in addition to execution, if we want to actually find what's the market value of our portfolio, we write a very similar method that just liquidates our portfolio. So liquidation of this portfolio is very easy. You just take every asset that's not a currency and you just negate it and then price it and you're done. And in fact, almost all of the operations we want to do in order to get our market prices, our unit prices, our market values, our P&L, our positions, all of these are just going to be simple group buys or constructing the other side of the trade or the other leg of the trade. Another interesting aspect of this is how we construct this trade is hidden behind this environment. So we can now break the assumption of linearity. And if it's the case that we are in Switzerland trading, we cannot buy certain assets with Swiss francs. If we want to buy oil, we have to buy oil. If we have to buy certain commodities, we have to purchase them in things like euro dollars. So if we happen to need to go through some intermediary, you take your Swiss francs and you turn them into dollars and you turn those dollars into oil, we can also represent this very easily with this structure, a multi-leg trade. For that, what we might want to do in order to get the grouping and the attribution correct is put one more level on our original data, just a simple range index with the trade identifier. And so, that's good, that's good. And let's see. And then for here, it's because we lost the level here. So here we gotta throw this back in. So here, and this is why you have to do this programmatically, because otherwise this is a real pain in the butt. But if we do this part programmatically, and now you can see we can group by the trade, and we could figure out, what is our net position for a given trade, or we could attribute our P&L or our market value down to the trade level. And as long as we do this part correctly and do it programmatically, which is a very small part that we're simplifying for convenience right now, you can see that we can work very nicely with foreign data and we get some immediate consequences of this, some immediate positive consequences of this. It turns out that most of the financial analyses that we'd want to do for this portfolio are actually as simple as this. Construct a unit portfolio, just take all the assets, create a series with values of 1, price it, and that gets you unit prices, so you can do things like 30 days return, 60 days return, all of that stuff. Now, since we've got that problem mostly solved, I want to talk about an even harder problem. And this is a genuinely hard problem that I do not have a good answer for, even up to including if we had the ability to upstream some changes, because I don't even know what the changes would have to be in pandas to support this. Oftentimes when we talk about pandas, we talk about it as a tail-end analytical tool. What does that mean, tail-end analytical tool? It means that we've done some sort of work, and at the very end of that work, we come in with our pandas code and we do some analysis. What does that prelude, what does the work before the analysis look like? Data collection is a big part of it. In general, pandas is something where we've done all the data collection, all the data is there, it's in maybe some other format, CSV, Parquet, it's in SQL. We pull it into our pandas structure and then we do our analysis. But we very rarely find that we do a little bit of work in pandas and then we create more data and do a little bit more work in pandas and create more data. In fact, if you really think about it, how often do you grow a pandas data frame? If you're using pandas the way that many of the core developers say you should, you're probably treating the columns of a data frame as immutable, especially if you're using a Jupyter notebook and you don't even know, if you mutate a column, you're not sure, did I run that cell once or twice? Did I mutate it once? Is it the right value? You're just adding extra columns onto the end of the thing. You're just growing the thing or dropping columns or swapping out columns. But how often do you grow it in terms of the number of rows? If you really think about this analysis, what we're going to do in some core simulator loop is we're going to take some initial trading balance. We're going to do some analysis on the market to say the top 40 performing names are this, equally weight and purchase those top 40 names, and we're going to end up with a pandas data frame with our trades that have 40 more rows. Then we're going to do that again the next month and the next month and the next month, and we're going to want to do this financial analysis on the result. We're going to grow that pandas series over time. Now, does it make sense for the strategy to want to look at the past trades? Of course, because if we've lost an enormous amount of money so far, maybe the strategy should be aware of that and tell us, hold on a second, something's going wrong. Let's do something different. Let's halt trading. Let's add in some additional mechanism. And that's a very reasonable thing that a human being would do, because if you're getting on the phone making these trades every day and you see that your portfolio is doing very poorly, you're not going to just continuously execute the exact same strategy. You're going to change it up. So it's something likely that you'd want to encode in your strategy, which means that you're going to have a pandas series or pandas data frame, in this case a series, that you're concatenating to every loop through your financial simulator. It is extraordinarily slow to grow these structures in place. And the reason for that is, if you think about what pandas originally was built on, it was built on NumPy and D-arrays. Of course, now we have the Arrow backend, and there are some options in Arrow, as I'll show you, that make certain parts of this problem easier. But what is a NumPy and D-array? What is that foundational piece that pandas was first developed on top of? It is an interpretive view of raw memory. So you have a memory address that starts here, some amount of data, and you're interpreting that with a D type. You're interpreting that with a shape. Subject to that, there's some striding and some size. Well, how do you append to that thing? You have no idea what's sitting in memory after that thing. NumPy and D-arrays and pandas.Series and DataFrames have no notion of a capacity separate from a size. The size is the capacity. This is why you cannot append to the thing without making a full copy. And now what you're thinking is, in a loop, for my strategy simulator, I'm going to identify my strategies, create new trades. If I append to a pandas.Series in a loop via concat, this will be so atrociously slow, you don't even know. I'll show you some examples of this, because I have some timings of this for another presentation I gave. This, if you're still trying to wrap your head around this is very similar to the problem that you have in pure Python, where the Python core developers tell you, you know what, if you want to take a string and you want to concatenate a string, do it with .join. Don't do it with plus equals concatenation in a loop. Don't do it with the sum function. In fact, there's a very shallow error message that you'll hit that'll say, no, don't do it. You can even comment that out. It's like a one-line to comment out and let sum actually sum strings. But the reason for that is, this is the difference between the naive approach and the .join approach. It's actually quite rare for us to see that naive approaches are, what is that? 10, 100, 1,000 times slower than non-naive approaches. 3 seconds versus, what is that, 4,000ths of a second? This is what happens when we try to do this with a Python string. Now, if we try the same example with, say, a NumPy and D array, so what we'll do is we'll create a bunch of NumPy and D arrays. We'll create 1,000 that are each 1,000 in size, and we'll do a couple of different operations. We'll first H-stack them over and over. So we'll H-stack one, then H-stack another, then H-stack another. And in each case, we're going to reallocate and recopy the memory. So this is going to use, probably, assuming that the memory is actually freed, and ignoring things like fragmentation, at least double the total memory of the structure itself, versus if we construct a Python list and do one array operation at the end, versus if we use a built-in array from the Python standard library and append to the built-in array and then turn that into a NumPy and D array. And it's quite rare for us to see examples where the Python standard library actually beats the pants off of NumPy 7 times faster. Appending to a NumPy and D array via H-stack approach is atrociously slow. This here is the speed difference between doing one array at the end versus doing them piecemeal, which is what we'd have to do in this example, because we'd have to get one trading analysis, then another trading analysis, another one. We have to do it day by day, or whatever date we're rebalancing and starting our trades on. And so what are we going to do? We can't grow this thing in space. We can try the exact same example in pandas. We'll create a bunch of pandas.Series. We'll give them a very simple date-time index, and we'll try a one-at-a-time concat. We'll try appending to a list and then a concat at the end. We'll even put them into a dictionary and then perform a series construction from that dictionary. And we'll concat them one at a time, and we'll see just concating pandas.Series, growing a pandas.Series in place is very, very, very slow, and it will destroy the performance of this project entirely. This is why we're at a crossroads here, because on the one hand, pandas is a tailored analytical tool. So building a library that creates new rows for an existing series or data frame, if it does that in a tight loop, which is necessarily the case for our simulator, we're going to have terrible performance. But we are only using pandas in the first place to get good performance. In fact, we may discover that as a consequence of the atrocious speed of growing these things, because the only way we can do it is to make a full copy over with the extra values every single time, we might have been better off using pure Python. But here's the problem. We cannot solve this problem with pure Python, because then we have to recreate all of group by. Do you really want to sit there and implement .group by sum that you get on a pandas.Series or a data frame in pure Python? Do you really want to implement like .pivot table on a list of Python tuples? Of course not. So we're at an impasse here, because we want to use pandas not only for the speed, but also the convenience of the API and how nicely it maps to these financial problems, especially the financial analysis problems, but also we want to grow the thing in space. Now, I'll go through the remainder of these details fairly quickly, but you can see Arrow actually provides us with something of a solution for this. Now, unfortunately, the solution is not available via pandas, but we can do something very similar. Arrow has the idea of an array being formed out of many different record batches and providing you a contiguous view, or something that looks like a contiguous view of one array where it's actually multiple batches that have been read in. Because what is the premise of Arrow in the first place? It's that if we want to move data between different systems, we're paying an enormous amount of cost to move that data because we're copying things. So how can we create a data structure that avoids copies at all cost? Well, if you think about it, if you're loading data, it's very common that you might load data from this CSV file and load data from this CSV file and load data from this CSV file. And Arrow, again, is going to say, you know what? You're probably wasting a lot of time doing those 3 loads and then copying them into one structure. So instead, I'll give you something that's kind of like, I don't know, it's like there's a term for this. There's a linked list variant where you have individual streams of that linked list and you link together larger portions of it. But this is basically what the record batch is. And so what PyArrow gives you is a chunked array, an array that can be broken down into parts where it looks like it's contiguous, but it's actually chunks. We don't have the ability to use this from pandas. If we did, then we could have a pandas series that you could seamlessly append to, because you just append a new chunk every time. And if you think about the nature of this analysis, what you're probably doing is you're probably doing monthly rebalancing, so a couple of days of performing the trades every month in large batches over just few total batches. How many total days are there in 10 years? 3,652 or 3, depending on if you caught, well, hold on, is it necessarily 2? Because the leap years are every 4 years, so you can never catch more than 2 leap years in a 10-year batch. That's for you to figure out. Anyway, we could do something like that, and we actually will get much greater performance. We'll get closer to the pure Python performance because we're not making these copies. So what we're going to do instead is something that is a little bit weird. When we perform the analyses on our pandas series, we're not going to set our API to operate on a pandas series, because fundamentally, we can't grow the thing in place. So we'll end up with hotspots in our code where concatenations are just going to be smeared all over the place, and the performance will be terrible. And there'll be no way for us to say, oh, drop this one piece down to C. It's everywhere. The problem is everywhere. And fortunately, we can't use the Arrow chunked array, but we can do something very similar. If we're computing, say, the market value, what if we compute this off of a volumes where this is a list, a Python list of series objects. Now, we could subclass list, we could subclass pandas series or DataFrame in order to give us the ability to do something similar to the chunked array. I do not know how much complexity it would be to actually make that work, and I don't know how much work it would be to keep that working over multiple versions of pandas. And so, as an expedient choice, maybe what we're going to do is we're going to keep things very, very simple. If a user can understand that some tool takes a series as its input, maybe they can understand that some tool either takes a series or a list of series, and then here you do something like, if is instance, volumes, iterable, or actually, if it's a series object, then you do something like this. And this is quite reliable and not particularly ambiguous. So you give them a little bit of convenience around here, and then you force everything to operate on lists of pandas series. That way, in the core of your simulator, you can just append to this structure, and then separately, external from this code, you can then, with whatever expedience you need, perform concats in order to collapse this. Because obviously, anytime you're doing an aggregate analysis, you're gonna have to do that aggregate analysis on the concated result if it needs all of them, or on each individual component. Well, for the most part, things like execute and price don't need to concat the thing ahead of time. I can just do an execute, execute, execute down each one of these series. So the only time you have to concat is really on the user side when they want to do the financial analyses. They want to see what's my market value, what's my position or whatever, or what's my average price or whatnot, any aggregate that needs to see all of them. But what you could then do is you could sprinkle in those concats to reconsolidate these things on the user end where they see their performance problems and not put it in the library. This leads to a fairly clumsy library because now everything has to work on lists of series, which is a very odd data type. I don't think you've probably ever seen a function that works on a list of pandas series. But if you think the arrow analogy, this is basically the idea of doing a chunked array, but we're just doing it much more clumsily at the pure Python level. Fundamentally, however, we can actually get this to work, and I think we can slide this by a user for the most part, because obviously if we do just a little bit to sand down the edges of this, they maybe won't notice that. So this brings us to the last portion of what we have. I want to represent a simulation with a strategy. So how do I represent the simulation strategy? I know I can do the financial analyses. I know those will be using only as their entity that environment, which will probably be a data frame or a series, and it'll generate as its consequence a series with just the volumes, with the executed side, with all the legs of the trade. How do I actually model the rest of this? How do I give you the ability to model a strategy? Well, there's one interesting design consideration here, and you'll see this as we come up. Generally, the one feature that, like I was looking at the PyTorch documentation the other day. This shocks me. If you really want to see a lot of Python code written by people who don't seem to really know Python, look at the PyTorch documentation. I don't know if that's controversial to say, maybe it is, maybe it isn't, but it's like, you'll read that and you're like, folks, this is a decorator. What are you doing like in reinventing decorators in the PyTorch tutorial? It blows my mind. And one of the ones that I see all the time in that documentation is, does nobody know what a generator is? If you're training a model, and one important aspect of that means you need to return to the Python level. And in the Python level, you need to decide if you keep going or not, because, for example, your training has hit some metric for the correctness of the predictions that it makes. And there's Python code that's determining whether you keep going or not. That is not a keyword argument. It is a generator or a generator coroutine. And in fact, pretty much any problem that we look at that we would call an agent model, or a simulator, or a backtester, where, and this is an important qualification, where there necessarily must be work done in the Python level, either because there is no closed form solution for this, or because we need the generality of pure Python in order to implement some aspect of the simulator or the backtester. This should always be modeled as a generator coroutine, and I'll show you why. In general, if we think about what our simulator would look like, it's actually a fairly straightforward entity. If we want the simplest possible thing we can do, what we'll do is we'll model the simulator as a coroutine. So this thing will loop forever. Each step coming into this thing will take in some external data, maybe whatever the updated environment is, so that we don't have to pre-create the entire historical environment, but we can kind of load those in piecemeal. We don't have to pass this in as an argument here. And one note that we can see is when we look at the design of generator coroutines in Python, it's very common that whereas in a Python function, your data are usually positional arguments and your modalities are usually keyword-only arguments. But in a coroutine, usually the keyword arguments, or sorry, the arguments to the coroutine itself are modalities, and any actual data is passed in via the .send mechanism. And so I think the environment is data. It's not some modality for this. That would be some kind of other modification on how we use the environment. So we'll do something like this. And on the other side, we actually want to yield out the state. So this is pretty much what a simulator looks like. You get in some information that gets fed into the simulator, and you yield out what the state is. And if this is an agent model, here, some kind of strategy simulator, then the strategy is also an inference structure like this, and what we have is something like this. So here, we'll ask the strategy. Actually, we need to send into the strategy the environment. And the state is some function of the desired actions and the previous state. So if we think about this, the structure is quite straightforward. We have a simulator that represents the loop. Every day or every unit of time, we give it some additional information, what the market environment looks like. That gets passed into the strategy entity, and the strategy entity says, okay, I get some market environment. Maybe, if we think about this, you probably also want to know what the previous state is. So I get the market environment, and I get to see what my portfolio looks like at some point in time, and I yield out what I want to do. The simulator takes what you want to do and then decides whether you can do it or not, and then should give you some feedback. And so these two pieces together give you pretty much everything that you need. For example, if you said, I want to trade into a new name in my index, but the actual historical market data shows that there was not enough trading volume for you to perform that trade entirely on that day, or for whatever reason your strategy needs to break that down, what you would do is you would say, okay, take those desired actions, execute the parts of the trade that you're allowed to execute given the historical data, kick back into the strategy that it wasn't fully executed, and the strategy says, oh, I see that my state is missing some volume if I want some weighting of my portfolio, and then gives you the extra actions. And naturally, you'll see then that strategy will then split that execution over multiple days. Now, there could be some small details to this. For example, what is the time ticking? Is the time ticking for this thing, you pass in an environment for each day, and then you get something back, or is there like some kind of intraday? All of those are small details for us to change. Because, for example, we could do something like this, 2 loops here, and we could say something like, let's do something like this. Well, I'll show you this for a moment. So you can do all sorts of little mechanisms. There's one detail that we're gonna have to fix here. So something like this. And this should actually be a 2 time delta. We want to do it this way. So you might have 2 layers of loops here. You might say, okay, I get in an environment with a particular date. That's maybe the beginning of the month when I do my rebalancing. If you look at mutual funds and things like that, they do a lot of rebalancing on these monthly boundaries or yearly boundaries. So I pull in, I give you my actions for that rebalance, and then there's an inner loop that says, okay, these are all the days in between, and that's what I'm trying to continue to execute to get to my model portfolio, what I want my portfolio to look like. And then here, you can imagine that this thing might also loop forever and then pass in that information until here, this might loop like this, until desired actions is none, and then breaks out of this loop. So we can model all sorts of small details here very easily. So maybe something like that. You know, we loop forever. Where we put the timing here, we'll talk about in a moment. But we could loop forever and then indicate, okay, we're done with all of our actions for this particular day, or we're done with all of our actions, and then trigger that in very simple ways with just 1 line of code or small changes here. Now, when we think about this tool, what we might think about is, at what point is the end user actually going to write code? Like, are they going to write the simulator? And in fact, in our experience with this, we discovered that the simulator itself is something that you really need to know a little bit more about coroutines to get this thing to work. In fact, for example, one of the problems that we all know that Python generator coroutines have is if I have a coroutine that looks like this, that takes some input value, and I create an instance of this thing, and I send in whatever my market data is, I get an error. Because I can't send a non-none value to a just started generator, or a just started generator coroutine, or a just started asynchronous generator, or asynchronous task, or a just started asynchronous coroutine. There's a modality here, specifically that the design of generator coroutines in Python was such that you have to emit a value before you can receive a value. And this creates a certain modality. There's necessarily an ordering to this because it's serialized. You have to do one first and the other next. Either emit first or accept. And the Python core developer said, emit first, accept second. But what this means is we can always identify whether we're at the beginning of a coroutine, whether we like it or not, because we'll error out. If we're at the very first step, we can't do an ascend, we have to do a next first. But if you think about these entities, and here let's make this an infinite loop. So we can do whatever we want after this precious first step, but this first step is special. But if you think about a simulator or an agent model, usually there's not really a modality on the very first step. If you think about a game, however, there often is. Think about this. You're playing something like hearts or spades with your friend. And if you ever played a game like that, one of these matching games where you have to play cards on the table, there is a distinction between the very first person who goes and every person who goes after. Every person who goes after just tries to match whatever they see on the table or exceed it. Or if you're playing Uno, you have to match the color or the whatever of the card every other person. But the very first person does something different. They flip over a card of the deck. They play any random card from their hand. They have a visible modality for where they're first. There's a different thing that you do if you're first than if you're not first. But With those exceptions, for the most part, things like these trading simulators or many agent models, there really is no difference between if you're at the very beginning or if you're somewhere in the middle. There may be a difference if you're at the very end, but typically we model these things as infinite sequence. Therefore, there is, by definition, no end. This is why, very commonly when we see these structures, what we're going to do is we're going to eliminate that first modality. We're going to invert the ordering here. So instead of first emitting and then receiving, we first receive and then emit. And this is a very common little decorator that you see that we write. So we just take this coroutine, we create it, and then we advance it one step, what people often call pumping. And just to make this moderately complete, we do something like this. There we go. And now we have something where we can no longer observe that first modality. The thing always accepts a value first and then allows you to do whatever you want. And this is likely what we want to use for any kind of simulator where, unless the nature of the problem says there's something different about the first actor, which again, in many games, the first actor has a different set of choices than everybody subsequently. Unless that's the case, this inversion is going to be important. And to make this a little bit easier for users, we might do something like this. So here, this could be something like strategy equals. And then we just tell them, here's a decorator. And they don't know any different. You just say, OK, here's a decorator called strategy. Put it on top of all your strategies, and everything just works. There's maybe one other small detail. Typically, when we do these, we have a dummy yield here. So this is the first input that we take, but this is a dummy yield. It doesn't yield anything. And these are each incremental input and each incremental output that we give. And so here we invert this. So it's very likely that we want to do something like this for our simulator itself. So the way we'll make this look is we'll do something like this. We'll call this pumped, and we'll call strategy is just here. We're really going to pull a fast one on our users because they're going to think this is something really important, but it's not. It's just our pumping of our thing. And then, of course, we're just going to use this again here, even though that's not a strategy. And now we just have to make some small modifications on this so that, for example, we get the very first environment and state, but we yield a dummy. And then we yield whatever actions we determine, then get the new environment in the state, then yield any actions we determine and get the new environment state. And it's likely that we'll have to do some composition here. Unfortunately, I gave a presentation a while back about this, but the pumping problem is very difficult to do on asynchronous entities. For the most part, this problem doesn't really have any exposure to the asynchronous universe, because if you think about it, the speed that you're going to get out of this thing, you got to do the analysis day by day by day. You can't parallelize that in fashion. You can't do tomorrow before you've computed today, because what tomorrow is going to be based off of is what happened today. And so as a consequence, if you need to get speed here, likely what you're going to do is use something like multiprocessing, and you're going to splay out the analysis. You're going to do some kind of search of some hyperparameter search of your strategy. So you're going to say, oh, my strategy assumes that we always keep 10% of our total balance in cash. But what if it's 15% or 20%? That's 3 strategies, 3 processes. You run them all at the same time. You're unlikely to implement parts of the strategy in some sort of concurrent mechanism, because I don't see how you do that. It's fundamental that tomorrow's operations are based on today. And so I would doubt that unless there's some data loading that has to happen here, you'd see much asynchronous work here. And even though you might see that asynchronous stuff, like if you needed to use HTTPX for some data loading or AIOSQL for some data loading, it's unlikely you would do that. Instead, very likely, the actual ordering of the steps of the simulation are necessarily going to be serialized. And then everything else is just kind of in its asynchronous land, but you're still locked on each step of the simulator. And so this more or less will give you what you want. The combination of this, together with your business model, will give you more or less what you look like. Now, I'll give you a little bit of pseudocode to show you what this would look like all in. At its core, what is the strategy going to look like? Well, the strategy is going to be, here, a simple strategy. An environment and some state that you get each step, and then you tell it what you want to do. And what you want to do is perform some trades. How do you want to perform those trades? Well, what you might do is you might ask this environment, which remember is an opaque object, for a unit portfolio. Here, this means that your environment class needs to have a little bit of a large API here. it needs to be able to tell you, for example, what all the assets that are tradable. And you can think that the strategy itself may not be able to know that. It may be the responsibility of the market to tell you these are tradable assets as of a given day. So unit portfolio would just give you a pandas series with all of the traded assets in unit quantities. Very simple entity. Price gives you the ability to price these things. And so that's just that multi-index.lock operation that tells you what those prices are absent the multiplication that you do. So you might have that here. You might have execute, which basically prices, by the way, here, this should be on some volumes, which remember, if we really want to do this right, we might do this, return a list of pandas series. So we might have execute, which, again, you can see this is a little bit clumsy, but there's really no other option. Goes through each one of these and yields out the corresponding side of that trade. If you give it AAPL, it tells you how many dollars were on the other side of the trade. And you probably also need something like liquidate. Because if you want to figure out what the market value, what is the market value of something? It's what you would get if you sold the entire thing today. So that just means take my holdings or take every single trade, reverse it except for the currency trades, and price those. So here, this is just reverse and price. And this is just price and reset asset. And here, of course, something like that. So you have those four pieces. So it's a somewhat large and somewhat asymmetric API, but it's still quite simple and covers a number of different cases. Because you can see here, there's no linearity based in this. The unit portfolio is a unit portfolio for the perspective of saying, well, what is the returns on something? Well, it's just whatever one unit. Generally, we'd assume that it's whatever one unit would be traded at today versus whatever one unit would be traded at 90 days ago. And for those purposes, we may assume linearity. And we take a unit portfolio. We could price the unit portfolio. Obviously, we'd have some modalities for doing this some days in the past. So here, we'd be able to price the thing today versus some days in the past. You divide that and subtract 1, and these are your returns. And again, this is actually fairly straightforward pandas work. You're just pricing things, you're just constructing pandas series, everything's just operating on pandas series, and you get your returns here. The one kind of clumsy thing here is that this division won't work. Because remember, we return list of pandas series, so we lose some of those operations. So what that probably means is we'll need to extend certain parts of our API in ways we might not otherwise want to. Instead of making this price on one date, we might instead give us the ability to price on multiple dates and return one list of pandas series with an extra index level or that in the date index, and then do a group by here. And so here, this might actually need to be written as a group by date, and then an unstack of, or here, an unstack of the date and then a division. And then here we, divide. I don't think we can do that. I think we have to do, S whatever divided by S whatever minus 1. So here we might need to do that just to make this a little bit more convenient. So we end up with somewhat strange structures. And of course, the other thing we have to do here is that pipe won't work. So we'll have to do the concat here just in case, just to collapse these. So we'll have to do a concat there. I think that's a little bit better than the other concats that we need. So this means that the API is going to be a little bit richer than we want it to be. It can't be as incremental because in some places, just moving between the series and the list of series is just so clumsy that we need to add in extra keyword arguments to handle that internally. But there we have returns. Based on these returns, we can figure out what our weighting of our portfolio is. These are the things that we want. If we want the N largest 20, this is the top 20 returns. And then we just take whatever our state is, whichever our portfolio is. Maybe this needs to be concated. And we could compute the market value of this, which does not need to belong anywhere except at our level. So we could have a convenience level that does not need to be part of the core library level for doing some things like that market value computation. And so we can keep that very shallow and very presumptuous about what the data looks like because it'll sit really close to where the foreign data looks like. And then, take this and then figure out how to divide that by the number of entities we have to get what the model portfolio looks like, and then execute those actions. And for the most part, you can see, even though this is pseudocode, it actually gives us an enormous amount of generality, despite some of the areas where we just run into limits with how we can use pandas. We can, for example, arbitrarily decide what we want to trade into, arbitrarily decide how we want to compute that using just regular pandas mechanics, just that one tiny unfortunate consequence of sometimes we need to do a concat in order to get that to work properly, or we have to put a for loop on top of this thing. And for the most part, if we actually measure the speed of this, because I built a system like this, we'll discover that except for small hotspots like the multi-index lookup being slow, which we can drop down to Python, the performance of this will actually be moderately good. In my tests for some system that looks like this, we're able to process 1 million trades off of 1,000 units, I think it's 100 million rows of pricing data against 1 million rows of trading data. We're able to do all the financial analyses in like 2 or 3 seconds, which is about the same speed as the read pickle operation. So there's still room to get that down to under a second, but still, for what we're looking at here, that's pretty realistic, maybe a 10-year portfolio analysis with some kind of strategy. And we run into certain problems. You can see that building a library on top of pandas is not as easy as you think. There's actually a lot of very small, fine details that we have to worry about in terms of how this is going to be used and in terms of how we structure the inputs and the outputs to make this feasible. I discovered in this that I thought I write a function that takes in a pandas data frame, f input is df, return a df, assume the columns name something, but all of those assumptions melt away, and you actually need a very delicate hand in order to do this properly. One thing that sadly I have not really seen in any code that uses, any code except maybe very popular libraries that accept pandas data frames, and even then, some of the plotting libraries that take pandas data frames and some of the machine learning libraries like pandas data frames as input, they're very presumptuous about what these things look like, what the shape of these things are. And I don't think they need to be that way. I think there are actually approaches with just a little bit of delicateness for you to solve this. And so with that said, thank you all for joining us for this presentation. This has been Simple Simulators with Generator Coroutines and Pandas. I'm James Powell. Thank you, everybody, and I hope you enjoyed.